Okay, so it's 1 minute. We can start. I am very happy to introduce for our seminar Ines Kath from Greifswald, and she will talk about non-reductive pseudo-Riemannian symmetric spaces. Please.
So thank you very much for the invitation. And I think a seminar called Geometry with Symmetries is the perfect place to talk about symmetric spaces. And I would like to use this opportunity to promote pseudo-Riemannian symmetric spaces a little. So rather than presenting a single result, I want to give a more introductory overview. So I find this subject interesting because pseudo-Riemannian symmetric spaces arise naturally, and although these objects appear rather simple, so there are many basic questions which are unsolved. So a pseudo-Riemannian manifold is called symmetric space if for all points of the space there exists an involutive isometry that has this point P as an isolated fixed point. So it is called reflection in P, since indeed it is a point reflection in P along geodesics locally around P. So symmetric spaces have special curvature properties. So it's known that the covariant derivative of the Riemannian curvature tensor vanishes. So I'm sure you're all familiar with the Riemannian symmetric spaces, such as spheres or projective spaces or Riemannians, and all these Riemannian symmetric spaces have pseudo-Riemannian counterparts, such as de Sitter spaces, anti-de Sitter spaces, or pseudo-Riemannian Riemannians. So all these spaces have a semi-simple isometry group. So however, the world of pseudo-Riemannian symmetric spaces is much richer. So in this talk, we will focus on the complementary case, namely on symmetric spaces whose isometry group is not semi-simple. So let me give a few examples. So we start with some easy example, but an important one, namely with Lie groups equipped with bi-invariant metric. So bi-invariant means that the metric is invariant under left translations and under right translations, the group. So this property implies that the inversion map is an isometry. So hence the inversion map gives us the reflection in the identity element. And if we take any other element, say G, then the inversion or the reflection at G is given by, or is obtained by conjugating the inversion map by the left translation with G. So, okay, so of course, we have as examples, we have semi-simple groups with the killing form, or the metric which is induced by the killing form. But here, we want to concentrate on non-semi-simple groups. So as an example, we have the oscillator group. So what is the oscillator group? So it's easier to describe its Lie algebra. So here I consider the four-dimensional oscillator group. The Lie algebra is spanned by four vectors, z, x, y, and L. So z spans the center. So x, y, and z generate the Heisenberg algebra. And the vector L acts on the span of x, y by infinitesimal rotation. So these are the Lie brackets, and it's called oscillator algebra since it's related to the quantum harmonic oscillator. So the Lie algebra is spanned by the identity, the position operator, the momentum operator, and the Hamilton operator is exactly isomorphic to this oscillator algebra. So here we can define a scalar product on the Lie algebra. So I only wrote here the non-vanishing scalar products of basis vectors. So Z and L are light-like and dual to each other. And the scalar product on the plane spanned by X and Y is the Euclidean product. So then one can check that this scalar product is invariant under the adjoint representation. So it defines a bi-invariant metric on the Lie group. So we get a bi-invariant Lorentzian metric. The signature is Lorentzian. Z and L are isotropic, and on the orthogonal plane we have a Euclidean product, so it's Lorentzian, and the ad invariance implies that it is bi-invariant on the group. And the group itself is a semi-direct product of the three-dimensional Heisenberg group and the real line. Yeah, the next example. Is an example you might know. It is known as symmetric plane waves. So here the underlying manifold is R n plus 2. And with coordinates u, v, and x1 to xn. And the metric that we want to define depends on parameters mu and nu, and it has the following form. So it is light-like in v direction, and this green part in coordinates u and v gives a Lorentzian part, that's Lorentzian signature. And then we add in this middle part, this blue term, which is simply a Euclidean metric. And we have to say what this function h is. So this h depends on the parameters mu and nu. It is a quadratic polynomial in the x coordinates. With coefficients lambda I squared and minus mu j squared. So I cannot give the reflections here explicitly, but at least you can see that the covariant derivative of the curvature vanishes, since h is only a quadratic polynomial in the x coordinates. It's the only non-constant term here. Important thing to mention here is that this metric admits a light-like parallel vector field, which is unique up to scale. It is exactly the coordinate vector field of the coordinate v. So now we come to the general case. So answer the question, so how we can describe symmetric spaces. Which symmetric spaces are there and how we can describe them. And for the description, we use the transvection group of the symmetric space. So let X be a pseudo-Riemannian symmetric space. then we can define its transvection group. Yeah, it is generated by pairs of reflections. So Sx and Sy are the reflections in X and Y. And we consider the group which is generated by these isometries. So it is contained in the isometry group. But in general, the isometry group can be larger than the transvection group. So we know this. So essentially smaller. So it can have, the transvection group can have a smaller dimension than the isometry group. So we know this from the flat space. Yeah, there the transvection group is a group of translations. And the isometry group is larger, so contains, for instance, rotations and so on. But in the Riemannian situation, so this is the only case where this can appear. So if you have a non-flat space, yeah, maybe indecomposable, so with no flat factor at least, then the transvection group is or has finite index in the isometry group. So, but here we will see that this is, in general, this is not the case here. So if we fix a base point in the symmetric space X, then since the transvection group acts transitively on X, so that's what we can show, we obtain that X is a homogeneous space. So transvection group mod stabilizer. And moreover, we obtain an involution of G hat, namely, if we take an element of the transvection group, we can conjugate it by this reflection in the identity. So this gives us an automorphism of the transvection group, and this involution, it's an involution obviously, and it defines, induces an involution on the Lie algebra, G hat of the transvection group. So this means we can decompose the Lie algebra of the transvection group into the plus eigenspace of this involution, denoted by G hat plus here, and -1 eigenspace. And then we can identify the -1 eigenspace with the tangent space of X at this base point. And G hat plus is simply the Lie algebra of the stabilizer. So one important point here is that the minus part, so the -1 eigenspace of the involution, generates all of the transvection algebra. So this means that the commutator of the minus part itself is not only contained in the +1 eigenspace, which is clear since it's just an involution, but it is equal to G hat plus. So the metric on X induces a scalar product on G hat minus, which is identified with the Lie algebra, with the tangent space of X. And this scalar product is invariant under the adjoint representation of the plus part of the transvection algebra. And so we can here this inner product extend to an ad invariant inner product on the algebra of the transvection group. So we get the Lie algebra, we get scalar products on the Lie algebra of the transvection group. And with respect to this scalar product, our involution theta is an isometry. So in this triple that we get, transvection, algebra, involution, and scalar product is called a symmetric triple. And these symmetric triples are in one-to-one correspondence to simply connected pseudo-Riemannian spaces. So moreover, we can decompose our transvection algebra into a semi-simple one and or zero, and a Lie algebra that does not contain simple ideals. And we get so a decomposition into two symmetric triples. So the semi-simple case is well studied. All these symmetric triples are classified by Berger, so these spaces are well known. And here we want to consider the complementary case. We want to assume that our Lie algebra of the transvection group contains no simple ideals. So this is a standing assumption here. Yeah, what can we say about these symmetric triples? So in joint work with Martin Ulbrich, we proved that such a triple has a canonical structure of a quadratic extension of Lie algebra with involution by an orthogonal module. So what does it mean? So as a Lie algebra, G hat arises by two extensions. First, we extend L by A, so where we understand A as an abelian Lie algebra. So it's a module here, but we can understand it as an abelian Lie algebra. We have first an extension of L of this arbitrary Lie algebra by an abelian Lie algebra, and then we extend it again, namely by the dual of L, by L star, where we understand L star also as an abelian Lie algebra. Okay. So, and so in particular, this means that our Lie algebra G hat is, as a vector space, it is a direct sum of L star A and L. And the Lie algebra structure comes from, is determined by this extension. So we can understand these extensions as extensions of Lie algebras. So then we can define a scalar product on G hat. Namely, we have a scalar product on A, and we can add the dual pairing between L and L star to this. So L and L star are totally isotropic. And on A we have this scalar product given before on A. So, and moreover, the involution on this quadratic extension comes from involutions on L and A. So the plus one eigenspace is the sum of the plus one eigenspaces of the involutions on the summits here, and also the minus one eigenspace of the involution. So this defines an involution. And we can prove that if we start, or if we have a symmetric triple without simple ideal, then it has this structure. And moreover, we give a cohomological description of quadratic extensions. So we can describe these extensions by a certain algebraic object. And then this description leads to I usually see a classification scheme for symmetric triples, since in order to get explicit classification results in the form of a list or something like that, we have to compute this algebraic object, and this can be difficult. But at least for a small index and under additional geometric conditions, this can be computed explicitly. So let us consider some examples. We already know the oscillator algebra. Here we can observe that it has such a structure of a quadratic extension. The Lie algebra L is spanned by the vector L, and this abelian part is spanned by x and y. And the center is L star. And our ad invariant scalar product that we defined in the beginning arises in the way that I explained for quadratic extensions. We have the Euclidean product on A and the dual pairing between L and Z, which are like. And the module structure on A comes from the commutator. So L acts by infinitesimal rotation on A. So then we can define also an involution here on this Lie algebra, namely we have to say what is the minus one eigenspace and the plus one eigenspace. So we can see that the minus one eigenspace comes from L. So L, the involution on L is minus identity, and the involution on A is such that x is in the plus part and y is in the minus part. So this means that for the whole algebra, the plus one eigenspace is spanned by x. So it's isomorphic to R, it's one-dimensional. And then in this way, we get a symmetric triple. And we can form the symmetric space. It is now oscillator group mod R. And this gives a three-dimensional Lorentzian symmetric space. So we can modify this a bit. Namely, we can replace the Euclidean scalar product on A by the signature 1, 1. So Lorentzian 1. And then we have to modify also the action in order to get an orthogonal representation. So here we take infinitesimal hyperbolic rotation. So the same, but as a rotation, but without minus sign here. So, and in this way, we get another three-dimensional Lorentzian symmetric space. So then we discussed as an example the oscillator group itself with its bi-invariant metric. It is a symmetric space. And what is a symmetric triple, which is associated with the space? The Lie algebra, I told you that it has the structure of a quadratic extension. So we can see it here. I can tell you what L and what A is. So it is as a vector space spanned by one-dimensional L and corresponding L star, and a four-dimensional middle part A. And here I have to see what the involution is. It is minus identity on L, and it is plus identity on x1 and x2, and minus identity on y1 and y2. Oops. So, and again, I take as a scalar product the Euclidean product. And now I also have to say what the action of L on A is. It is again by rotation, namely by rotation in two-dimensional subspaces, the one spanned by x1 and y1, and the one by x2 and y2. So then the plus one subspace is A plus just, and we get in this way a symmetric triple. Now we have examples of Lorentzian symmetric spaces, and they are symmetric triples. And we can try to do this for Lorentzian symmetric spaces of arbitrary signature in for the general case. So we assume that X is a Lorentz symmetric space, intercomposable, so it means it's not the product of two symmetric spaces, and we assume that it has non-constant curvature. So we exclude the spheres and hyperbolic spaces. So then the transvection algebra has the same form or similar form as before, and we call it generalized oscillator algebra. Yeah, it again arises by this construction from L and A. L is here again one-dimensional, A is even-dimensional, and L acts on each R2 by a rotation or a hyperbolic rotation. So it can act by different velocities. So the rotations and the hyperbolic rotations can have different velocities, and these velocities mu I and lambda j are we know them already, namely the resulting symmetric space is exactly a plane wave, and these mu and lambda which appear here are the parameters in the metric. So, and as for the transvection group, so we know the Lie algebra now. The transvection group is a semi-direct product again of a Heisenberg group, now a higher dimensional Heisenberg group, and real line. So these spaces are called Klein-Warlock spaces, since Klein and Warlock classified Lorentzian symmetric spaces of non-constant curvature. And these are exactly these spaces. So I will see symmetric plane wave or Klein-Warlock space. So we now leave the Lorentzian setting and see what the extension structure of the transvection algebra implies for general pseudo-Riemannian symmetric spaces. So assume again that the Lie algebra of its transvection group has no simple ideals, and we know that it has the structure of a quadratic extension. And we consider first this Lie algebra L with involution. Then we have L with its involution, and we know that the minus part of L generates the Lie algebra. So the commutator with L minus is L plus. So it defines in a fine symmetric space called Y. And moreover, if we take the remaining minus part of the, so L star minus plus A minus, then this part is invariant under the adjoint action of G hat plus. So this implies a few things. So first, that the subspace defines the left invariant distribution on X. And this distribution is parallel. To see this, one should know that the holonomy representation of the symmetric space is simply the adjoint representation of the stabilizer in the transvection group. So this is not true for the isometry group, but it is true for the transvection group. So if the subspace is invariant, it defines parallel distribution. And the leaves of this distribution are flat. So this can easily be seen if we have to know that the curvature tensor is given by the commutator on a symmetric space. So we have the double commutator here on the tangent space, which corresponds to G hat minus. And then we use that A plus L star is two-step nilpotent. So the commutator of A and A is L star, and the one of A and L star is 0. So this proves that the leaves are flat. And in this way, we get a vibration. We see that X fibers over the space of leaves here. And this is indeed vibration. And the fibers, so to the leaves here, are flat and co-isotropic. So co-isotropic means that at each point, the tangent space is the orthogonal space of a totally isotropic one. Yeah, we can go back to our example of Klein-Wallach spaces. Here I wrote again the metric. I have to see again what the metric is. And here the leaves are exactly the U levels, the level sets of the coordinate U. So we discussed a lot Lorentzian symmetric spaces. Now I come to classification of pseudo-Riemannian symmetric spaces of signature 2n. It was first given by Kahn and Parker, but this classification contained large gaps, which was observed by Thomas Neukirchner, who improved all this, and this was almost correct. And then in joint work with Martin Olbrich, we did this classification in a more systematic way using this quadratic extension and the quadratic homology. So, and in particular, we found some small mistakes in Neukirchner's classification, but classification is always an iteration process, so it was almost correct here. So for example, if we consider only n equal to 2, so we have a 4-dimensional symmetric space, then from this extension structure, we know that L minus has dimension at most 2, since this follows, since L minus is contained in the tangent space, and the metric has signature 2, 2, so it can, and L minus is totally isotropic, so it can have only dimension 2 most. So this means L plus, which is a commutator of L minus, and L minus is at most one-dimensional. And this leads to our affine symmetric space Y. And this is equal to R or R2 or S2 or hyperbolic plane or the de Sitter space. But all these spaces considered without metric, so just as affine symmetric spaces. And then I also wrote the corresponding Lie algebra L here. So it can be R if it's one-dimensional, and if it is two-dimensional, it's R2, and otherwise it is the Euclidean, so the algebra of the Euclidean group or the pseudo-Euclidean group of R2 or SO3 or SO12. So this means that the transvection group is, in the first case, it's solvable and it can be nilpotent, in the second case, or it is non-solvable in the case where we have S2H2 or S11. And I also noted here the number of linearly independent parallel light-like vector fields, so the maximal number of linearly independent parallel light-like vector fields. So this is what we get from the classification in dimension 4. So I want to explain these symmetric spaces a little bit more detail. So if K is equal to 0, then, for example, so take the example that Y is the sphere, so S2, then X is diffeomorphic to the tangent space of S2. So, but the metric is such that the fiber, so each tangent space is isotropic. So we can embed the space in R3 times R3, like I wrote here. So we have on one factor, we have the usual embedding as a sphere. And and on the other factor, we have the tangent space. They are not orthogonal to each other, but we have the metric here. And the metric is induced by the metric on R3 times R3. So we get a one-parameter family of symmetric spaces, which are in fact extrinsic symmetric, which means that the reflections are restrictions of reflections of the ambient space. It's even more than just to be symmetric. So we get a one-parameter family, so this means for difference C, we get non-isometric spaces. So if K is equal to 1, we get also continuous families of metrics, which look like plane wave metrics. And here I want to give two particular examples, namely, I call these XH and XE. XH is obtained here for this particular H with epsilon equal to 1. and it is the hyperbolic oscillator group. So we replace the rotation by a hyperbolic rotation. It is a group with a bi-invariant metric. And yeah, we get for epsilon equal to -1 is similar space, but this is not a group. For k equal to 2, we obtain two single spaces. So they are Hermitian and again also extrinsic symmetric. So this is in signature 2, 2. And I want to also give for some examples the isometry group here, namely for Kahn-Warlock spaces. I told you that the isometry group can be larger than the transvection group. And here we get that the isometry group is a symmetric product of the transvection group and a subgroup, a compact subgroup of SON. Particularly, it is a product of K and R, and the symmetric product then of the Heisenberg group. So, and then for signature 2, in a joint work with Matti Lyko, we computed the isometry groups in signature 2, and yeah, for k equal to 1, we get that we call that G hat is solvable and non-nilpotent, and in this case, X is has a metric which is similar to plane waves. Then, with the exception of these two spaces, XE and XH, the transvection group is equal to the identity component of the isometry group. For k equal to 2, we get that the isometry group is much larger. It is not longer nilpotent. It is a product of SL2R and the transvection group. And for k equal to 0, so this was the case where X is a tangent space of a sphere or hyperbolic space or de Sitter space, then the isometry group or the identity component of the isometry group is equal to the transvection group. And we can compute the isometry groups for arbitrary signature. So if we use this quadratic extension form of the transvection group. So this is just an example. It's a straightforward computation. So besides symmetric spaces, we are also interested in locally symmetric spaces. So symmetric spaces which are only locally isometric to a symmetric space. And yeah, these are characterized by the property that the curvature is parallel. And in particular, we are interested in compact locally symmetric spaces. So examples of such compact locally symmetric spaces are obtained as compact quotients of symmetric spaces. Yeah, if we have a discrete subgroup of the isometry group that acts freely and properly on X, then we can take a quotient and we get a complete compact locally symmetric space. So conversely, every complete compact locally symmetric space arises in this way as a quotient. But unfortunately, in the pseudo-Riemannian situation, compact does not imply complete. So this leads to the following problems, the following questions. So which symmetric spaces have such compact quotients? Yeah, all Riemannian ones have compact quotients, but what is the situation for pseudo-Riemannian spaces, and which compact locally symmetric spaces are complete. These are two problems which I'm interested in. So for Lorentzian symmetric spaces, we have an answer. Even if we are interested here, we are not interested in the constant curvature case. Let me say what happens here. So for the Minkowski space, it's clear we have compact quotients. For the de Sitter space, the space of positive constant sectional curvature, one might expect that there are compact quotients, since SO1 n plus 1 has a lot of lattices. But of course, lattices need not to act properly on the sphere. So this is not an answer. And indeed, the answer is no. This was proven by Calabi and Marcus. They have shown that only finite subgroups of the isometry group can act properly on the sphere. And for the anti-de Sitter space, the answer is yes, if and only if the dimension is odd. So now let's discuss compact quotients of Kahn-Wallach spaces. So we may assume that gamma is contained in the identity component of the isometry group, since the isometry or the identity component has finite index in the isometry group. And for Kahn-Wallach spaces, here I wrote again the metric. We give a criterion for the existence of gamma in terms of lambda I and mu j. So we can see exactly when there exists compact quotients for which parameters. So here we consider let me explain this in more detail. We have two cases. The first case is that the projection of gamma to this R factor of the isometry group is dense. And the other case is that it is not dense, so it is discrete. So if it is dense, we can prove that gamma has a nilpotent synthetic Hull. So this means that it is contained in a connected subgroup of the isometry group, such that gamma is co-compact in this connected group. And we prove that this is the case if and or this can happen only if X is the Lie group, the bi-invariant metric. So case one is simple, so we get exactly the Lie groups with bi-invariant metric. And the complicated case is where the projection is discrete. So if the projection is discrete, I can explain only an example, so not the general theorem here. So let us consider the case where only lambda parameters appear. So that means that mu is empty. So it means we have only hyperbolic rotations. So then the space admits a compact quotient if and only if we find an integer polynomial which is normed, and the constant term is plus or minus 1, such that the parameters lambda come from the roots of this polynomial up to a factor r, the constant factor r. So this is only an example. We get as a corollary that for some choice, or a suitable choice of signs, the sum of these lambda I is 0. This is a kind of trace condition. And yeah, we can also solve this general case for where we have combined lambda and mu. So in general, in this case, the gamma does not have a synthetic hull, but it is contained in a Lie group with a cyclic component group. So now let us consider signature 2, 2. So we have now index 2, but small dimension, only dimension 4. So then it is clear that we have these two special spaces, XH and XE, and both of them admit compact quotients. So the hyperbolic oscillator group has lattices, and also XE, which behaves similarly, has compact quotients. And then Maeta proved that if G hat, the transvection group, is solvable, and we only consider discrete subgroups which are contained in the transvection group, such that the quotient is compact, then these are the only spaces in signature 2, 2. So this means for k equal to 1, so this is solved since in all other cases, they're different from XE and XH. The transvection group is equal to the identity component of the isometry group. And for k equal to 2, it is partially solved, namely only for gamma which are contained in the transvection group, which is smaller than the isometry group. And for the other cases, in a joint work with Matti Lyko, we prove that there are no compact quotients. Yeah, the idea here is, I can explain it only for k equal to 2. The other case is rather complicated. The difficulty here is that we are looking now for gamma in the isometry group, and unlike the transvection group, this group is not nilpotent, so gamma does not automatically have a synthetic hull. So then we assume that such gamma exists and take an arbitrary element of this gamma of this group. And then we know that this acts freely in the group, so it cannot have fixed points, which implies that 1 is an eigenvalue of the projection of gamma to the SL factor. And this holds for every element, so it also holds for the Zariski closure of the projection of gamma to SL. So it is contained in this one-dimensional unipotent subgroup of SL2R. And then we see that gamma is now contained in a nilpotent group, and there it has a synthetic hull. And then we can work with this group or with the Lie algebra of this group, and we use the explicit structure of the Lie algebra to see or to get the contradiction that it cannot happen. So it has to be transversal to the stabilizer, and such Lie algebra does not exist. So this is not very detailed, but I only want to say that the main idea is to use the synthetic hull to translate the problem on discrete groups to a problem on connected groups or Lie algebras. So the second problem is that one of completeness. So we know that in the pseudo-Riemannian situation, compact manifold is not necessarily complete. So a prominent example is Clifford pole torus. And even compact, locally homogeneous spaces are not necessarily complete. So our question is, if we now assume that the space is locally symmetric, can you then prove that it is complete, it's compact? So let's consider the Lorentzian case. So for constant sectional curvature, we know that this is true. This was proven by Carrier and Klingner. And if M is locally isometric to a Kahn-Warlock space, is it also true? It was proven by Leisten and Schlittner. Thomas is here, Anthony. So, and in the decomposable case, Arndt and Amuna proved that this is also true, but this is not yet, the result is not yet published. So it's a gray here. So. And in signature 2.2, we have only partial results. So which Matti Lyko proved in his PhD thesis. So for instance, if M is locally isometric to a space with a unique parallel like vector field, but if it's not equal to these particular spaces XE or XH, then it is complete. And if it is locally isometric to some of these exceptional spaces, then under the additional assumption that it is Kleinian, so this means that we already know that it is a quotient of an open domain of X by discrete subgroup which acts isometrically on omega, then M is complete. So finally, I want to say something about the fundamental groups of compact quotients. So, which means if you have quotient of X and gamma, so the structure of gamma. So we never really classified or tried to classify these discrete groups gamma. This would be too complicated, but we can at least say something on the structure of these groups. So maybe before I say something about our results, some history. If we consider compact flat Euclidean spaces, then we know that the fundamental group is torsion-free and virtually abelian. So the subgroup of translations in the fundamental group has finite index in the group. And for the flat Lorentzian case, we know that pi1 is torsion-free and virtually nilpotent, or virtually a symmetric product of an abelian group and a cyclic group. This was proven by Grunewald and Margulis. So in fact, they really determined all these groups. So this is just in this case, corollary of this classification. And our question here is, what is the structure of the fundamental group of a compact manifold that is locally isometric to an indecomposable, non-reductive symmetric space? And we can see this for Lorentzian symmetric spaces. So then the fundamental group is torsion-free and virtually nilpotent, or a symmetric product of the nilpotent group and a cyclic group. And in signature 2.2, Matti Lyko proved that it is torsion-free and virtually nilpotent, or equal to, or isomorphic to the symmetric product of N and the cyclic group. Okay. And what I want to say here.
Thank you very much, Ines, for the very nice talk. Any question? Can I ask a question? You have a result for signature 2-2 about completeness and so on. What is known in higher dimension, still in neutral signature? Something is known in general?
In general, no, I don't think so.
Okay, so
Marek can also say something about signature to something, also higher dimension, but only for index 2.
Okay. So for instance, if in dimension 6 is very, one cannot say anything, right?
Not in general.
Okay. Thank you. Any other question?
Yes. What is known about the Laplacian? Is there some Laplacian associated to these pseudo-symmetric spaces?
Yes, of course, there's some Laplacian. So, but
I expect this Laplacian doesn't have good properties, right?
Yeah. So it has good properties if we are in the situation that we have a Lie group with a biometric and modulo some lattice, some co-compact lattice. And we did this in dimension 4 for the oscillator group. Matthias Fischer, so we classified the lattices of this group, and then we determined the decomposition of the L2 space or of the right regular representation into irreducible subrepresentations, and this gives then the spectrum, can compute the spectrum from this. But we can do this only since, in the group case, since then the right regular representation decomposes into a sum of subrepresentations. This is not true for general symmetric spaces. And now with Margarita Kraus, we try and some examples to get to see what the spectrum of the Laplacian is, but it seems to be rather difficult.
Okay. Thank you very much.
So if there are no more questions, let's thank again Ines for the very nice talk. And
Thomas.
Thomas has a question?
No, I just wanted to say hello.
Oh.
Hi.
Nice talk. I'm